What else?
You ready to go, Slava?
Yeah.
Okay. All right, let's get started. So back to higher dimensional CFTs with Slava Rychkov.
Okay, so up to now I was taking kind of probabilistic point of view on my theories, and today I would like to introduce the operatorial way of thinking. So I would like to be able to view, I would like to be able to cut and glue my path integrals, and I would like to view my operators phi as operators acting in the resulting Hilbert space. So this is the language that was already used freely by Xi, and so if you are, I'm going to be a bit more pedestrian. So if you're not 100% comfortable with this, then you'll be able to catch up. If you think you are 100% comfortable, you will be able to see that there are some subtleties that you should be aware of. So so let me start just with something that we all know, we think we understand, which is quantum mechanics. So I'm going to take Euclidean quantum mechanics. And so I have just a one-dimensional system, and on this system I have some operators phi of tau, and I would like to be able to cut and glue my path integral, for example at time tau equal to 0, and I would like to be able to realize my phi of taus as operators acting in this Hilbert space. So so in this case, well, I know what my Hilbert space is. So if I'm just doing the quantum mechanics of one particle moving on a line, then this Hilbert space is just L2 of R. So we know what this Hilbert space is, but suppose that later on I'm going to do the same story for quantum field theory. So first for Poincare invariant quantum field theory, and then for CFTs. So in that case, when I cut my path integral, so we intuitively think that the Hilbert space that I get is some sort of space of states living on the surface, but we don't really know what this state is. So here we have explicitly it's L2 space. In that case, it's just some platonic object that we talk about, but we don't really know what it is. What I would like to do is to move this platonic object from being platonic to being concrete. And in order to do this, I have to first explain to you how I could recover this Hilbert space for quantum mechanics without knowing what it is. And so it's a nice exercise. So okay, let me first say what are we going to be aiming for. So we know that in quantum mechanics, so this is what we know, that if phi of 0 acts in the Hilbert space, which you obtain by cutting at time tau equals 0, then phi of 0 is a Hermitian operator. On the other hand, we also know that phi of tau in Euclidean quantum mechanics is obtained as e to the h tau phi of 0 e to the minus h tau. And so this is what you get by weak rotating. And so we know that phi of tau is not a Hermitian operator, but we have this relation that phi of tau Hermitian conjugate. Yeah, and also we also know that h dagger is equal to h. So phi of tau Hermitian conjugate is equal to phi of minus tau. So that's what we know. And so one thing in particular that we know is that by putting together these things, is that if we consider the following state. So I would like to be able to make sense of the following state when I take phi of tau 1, phi of tau 2, phi of tau n, and I act on the vacuum. And so let me take all of these states negative. So I'm going to take 0, larger than tau 1, larger than tau n. So let me denote this as tau 1, tau n. So what I know is that if I take the norm of the state, and the norm of the state is going to be, okay, so let me just denote tau 1, tau n, tau 1, tau n. So I compute the norm by taking these conjugations. So this is equal to phi of minus tau n, phi of minus tau 1, phi of tau 1, phi of tau n. So I know that this is positive. So this is what I know in quantum mechanics. So in fact, I can generalize this by considering a more general state, which is a linear combination of these guys. So let me consider a more general state, which is going to be, I'll denote it as psi, which is a sum over n. And here I'm going to integrate. So I'm going to introduce this object tau n, which is just denotes this n tuple. So I'm going to introduce a function fn, which depends on this tuple, and then with this state. So each of these states, which is just a linear combination, so I'm going just to take these functions fn. Since I would like my state to live at negative times, all these functions fn, they are only non-zero for negative times. So I also know that all of these states have positive norm, have no negative norm. So I have this constraint that that sum over nm integral d tau n d tau prime m f n complex conjugate of tau n f m of tau m prime. And here I'm going to introduce this notation. So I'm going to call this conjugate state, which is inserted at negative times, I'm going to call it, I'm going to introduce this operator theta, which inverts times. So this has to be positive, has to be non-negative. So theta is inverts times. And so this condition, written in this form, is known as Osterwalder Schroeder reflection positivity. So that condition over there, which I written before, which is just a condition for one two-endpoint function, is also called sometimes reflection positivity, but it's a strictly weaker condition. So this is the full reflection positivity, involves this sum of linear combinations.
Sorry, the bar should be to the left of theta, or somehow?
Could you repeat the question?
So there was a question about the bar, where I should put the bar. Oh, sorry, here this tau prime.
No, but also, if you look at the inner product is just tau, tau. It's not minus tau, tau.
So yeah, I guess what I didn't write it properly is that I should have what I should have said is that so you see when I take a complex conjugate of my state, I insert operators at minus tau a and minus tau 1. So what this notation means is that here I just have to evaluate the correlation function where I insert a bunch of operators at negative times and a bunch of operators as positive times, and at which times I have to insert them is dictated by this operator theta, which inverts times.
Saying in the special case of this, you said it's strictly weaker, there is no theta, and that's the correct version of that.
So
No, it's not. It's weaker not because I didn't write the theta there, but just because I didn't want to be pedantic. But it's weaker because I'm just considering one two-endpoint function. But here I'm considering linear combinations which involve 0-point functions, 1-point functions, 2-point functions, and so on. Yeah, so that's why it's weaker. So okay, so this is what we know, but now I would like to turn this logic around. So what I would like to say is that suppose that I don't know that my theory comes from quantum mechanics. Suppose that I don't know that my theory comes from positive definite Hilbert space, from Hermitian operators. Suppose that all I know is that I have a bunch of correlation functions. So all I know is that somebody just hands me a bunch of correlation functions, phi of tau 1, phi of tau 2, dot, 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 phi of tau n. So now these taus can be both positive and negative. And tells me, okay, construct a Hilbert space. You don't know the Hilbert space. You just have these functions, and you have to construct the Hilbert space. Can you do this? I say, I can do this. So if my correlation functions that you gave me satisfy this condition, so you see this condition, it does not refer to the Hilbert space. It refers to correlation functions, which I integrate with respect to arbitrary functions. And I just check that whenever I do this operation, magically the answer always comes out node negative. So I say, if somebody hands me correlation functions such that this condition is satisfied, then I can construct a Hilbert space. And how I can construct it, so this was the idea of Osterwalder-Schroeder. So if so I have these correlation functions, and if RP is satisfied, holds, then I can invert the logic and I construct my Hilbert space. And the way I'm going to do this is just I'm going to take so my Hilbert space elements, I'm going to denote it as F. So mathematically speaking, what I'm going to do is that I'm going to take a sequence of functions F0, F1, dot, 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 F2, dot, dot, dot. So I'm going to start with a sequence of functions. So it's a well-defined mathematical object. Now, for each of these sequence of functions f, I'm going to define my inner product. So I'm going to define inner product fg by this formula. Given a sequence of functions, I can compute the inner product. So okay, no, sorry. Here I had like f equals f, but now I can take here f and g, and I get a good inner product. So these are functions of times, yeah. So these are functions of times which are only non-zero for negative times. So f0 is a constant, f1 depends on one time, f2 depends on two times, and so on. So since I have RP, since by assumption I have RP, this inner product is positive definite. So I have a positive definite inner product. I have sequences of functions. Is this a Hilbert space? Well, not quite yet, because the Hilbert space is supposed to be complete. So my inner product, which is positive definite, gives me the norm. So I complete my Hilbert space in this norm. For example, I can start with finite sequences of functions, and I go to infinite sequences of functions. I get the complete Hilbert space. This is my Hilbert space. So I can construct the Hilbert space starting from just correlation functions. So this was the idea of Osterwalder and Schroeder, and applied to quantum mechanics, this is paranoid because we know what the Hilbert space is. But if you do quantum field theory, it's precisely the point. So you don't need to know what the Hilbert space is. All you need to know is a bunch of correlation functions, and then from correlation functions you can reconstruct the Hilbert space if you want it. So what I just described for you is a rigorous version of the statement that we use all the time. Is that if you take a space, if you take your full Euclidean space, you foliate it by lines of constant time. You take time equals 0. You insert a bunch of operators at negative time, and this generates for you a state living on the surface tau equals 0. So this is the language that you always use. And now, whenever you use this language, you can perhaps feel more comfortable because you know that this is what it actually means. So I guess you get the point, but let me write down, nevertheless, the equation. So so that was quantum mechanics. Now I'm moving to Poincaré invariant QFT. So for the Poincaré invariant QFT, I have a bunch of correlation functions, and I assume, so I would like to make sense of these states F, which are equal to sums of Fn x1 xn phi of x1 phi of xn acting on the vacuum, where x1 up to xn, these are some operators inserted in the negative half space. So I assume so this is the assumption called reflection positivity, that the inner product, which I define Fg, which is sum over n, sum over m, so here there was an integral. Integral, okay, I'm going to write it schematically, Fn complex conjugate Fgm. And here I introduce this important Osterwalder-Schroeder reflection operator, theta x1 ... phi of theta xn. So let me see. Let's see. Okay, Fn's depends on x's, and Gm's depend on y's. And so here I have also phi of y1, phi of ym, sorry. So I assume, so this is the assumption of reflection positivity. So operator theta in this case is the operator which takes a point with coordinates tau x and just flips the sign of tau minus tau x. So if this inner product is positive definite, so if I take f equal g, this has to be positive definite. So this is Rp. F equal g, it has to be non-negative. Then I can play the same trick. I can complete my Hilbert space according to this norm, and I get the Hilbert space of states living on this plane tau equals 0. So now notice there is an interesting technical twist here, is that my correlation functions in quantum mechanics, correlation functions could be true for any times, but I know that in quantum field theory my correlation functions are going to be singular at coincident times. Is this a problem? It's not a problem at all, because I can take these functions f and g to be zero, to be vanishing at coincident times. So if I take them vanishing at the coincident times, this integral is still well defined. And then, whatever happens at the coincident times is going to be taken care of during the completion procedure, when I pass to the limit, when I complete my Hilbert space with respect to this norm. So that's a very interesting technical point of the Strava-Rychkov construction, is that in Euclidean quantum field theory, if you take this point of view, you don't need to assume anything about the coincident times.
Often it's said that contact terms is a matter of choice. Does this choose a particular set of contact terms?
So the question is, does this, what does this, whether it, when I perform this construction, does it choose anything about the contact terms? Is this some sort of arbitrary choice or non-arbitrary choice? Well, I actually don't know.
The way you phrased it, it sounds like there's a canonical choice. There's a unique completion procedure.
Yeah, so Greg points out that since I'm claiming this procedure is unique, it means that it allows you to fix uniquely the contact terms. Perhaps, yeah, it's a nice observation.
Sorry, but is it really clear that it fixes contact terms? Because the completion is the level of state, not the level necessarily at the level of these. Does it actually follow?
So on the other hand, she points out that it's not clear to him that this fixes anything about the contact terms. So so we have heard two conflicting opinions, and my opinion is somewhere in between. But but I agree with both of my esteemed colleagues that this is a very interesting thing to think about. But let's proceed because Max?
I have a dumb question.
Yeah.
When you say complete, does it mean get rid of all the zero norm states? Or?
Yeah, so Max also points out that when you complete, you might sometimes end up with states of zero norm, and you have to quotient over them. Yeah, this is also another technical point that you may want to do.
I mean, this Hilbert space is huge, right? The one that you just f naught f minus 1. So it's not the same as L2 of R at all.
So to Max, it seems that this Hilbert space is huge. It's not going to be L2, but actually all Hilbert spaces which are separable are isomorphic to each other, so they are both equally huge. No, I think in this particular case, for quantum mechanics, you will definitely get just L2 of R.
Sorry, Slava. Perhaps I can try to clarify my question. To say that you can fix a contact term means you can actually integrate this current function for arbitrary f that behave, say, smoothly at coinciding points. Your completion at the level of the state. So I'm not sure what is the result of the test function f when you do the completion, right? I mean, it might be that they still have some fall off.
Yeah.
But not at arbitrary. It's not like I can take some arbitrary finite value at coinciding points. So for that reason, it's not obvious to me that the completion implies you can actually fix contact terms.
Yeah, so she points out again that it's not obvious to him that that since I initially start with functions which vanish at coincident points, and then I complete, perhaps I will get some functions that will not vanish identically at coincident points, but only to some finite order. But it's not clear if I will be able, for example, to integrate my correlation functions against test functions which are non-trivial, non-zero at the coincident points. I agree with that. So yeah, so in this sense, this is not really a full fix up of the contact terms. But let's keep going. So actually, what the reason why Osterwalder Schroeder came up with this construction is that at the time they were worried people were worried about what is the exact relation between theories in Minkowski and Euclidean signature. And so what they proved is that if you start with this RP assumption in Euclidean and under some extra technical assumptions, you can rotate your theory to Minkowski, and it's going to satisfy all nice axioms that people usually assume in Minkowski. So if, on the other hand, if you start with the unitary theory in Minkowski and you rotate back to Euclidean, you land on this reflection positivity assumption. So, and if you, on the other hand, if you take a non-RP Euclidean theory, then that theory might not even be rotatable to Minkowski, or if you try to rotate it, maybe you'll get something which is going to be senseless in Minkowski. So what this means is that if you are a real-time person, if you are a particle physicist, or if you are a quantum condensed matter physicist, then you should really ever care only about RP theories in Euclidean. If you are a statistical physicist, then you actually do have to care about non-RP theories in Euclidean, both about RP and non-RP. You know, I have a lot of interest in statistical physics systems, so I do care about non-RP theories. But in these lectures, nevertheless, I'm going to focus only on RP theories for three reasons. So the first reason is that many interesting theories are RP. The second reason is RP theories will satisfy extra constraints, as we will see, so which make them easier to study. And the third reason is that if you go to non-RP theories, so you basically lose the Hilbert space technology, at least the rigorous version of the Hilbert space technology. So you're on shaky grounds. So perhaps, in fact, if you know, in mathematics, when mathematicians say Hilbert space, they mean positive definite Hilbert space. So non-positive definite Hilbert space is an oxymoron. But there is a theory of non-definite, indefinite vector spaces, which are called Crane spaces, and perhaps they might be useful for the study of non-RP theories. But this has not been done, as far as I'm aware of. So it's largely an opal problem. Of course, this doesn't mean that, you know, some non-RP theories, for example, minimal models in two-dimensional CFT, some of which are non-unitary, are understood. But in general, if you look at general non-RP theories, then it's a very murky subject, which is underdeveloped. So I'm going to focus on RP theories. And so now if you look at this RP condition that FF has to be non-negative, so it involves arbitrary sequences of these functions f, and it might look pretty intimidating, and so you might wonder, okay, how easy it's actually to check in practice that this condition is satisfied. And actually, amazing thing about this RP condition is that it's relatively easy to check in practice. So RP is easy to check. Usually, and moreover, a nice thing about RP is that if you are studying some CFT, and if you know that your CFT arises as a critical point of some lattice model, it's enough to check RP on the lattice, because then it will appear CFT will inherit RP from the lattice. So you just need to check RP on the lattice, and it's usually very easy to check RP on the lattice. So for example, if you take, so just as an example, if you take some sort of if you take some sort of cubic lattice model, for example, Ising model or its relative, and then if you know statistical physics, you know that statistical physicists usually think about these lattice models in terms of transfer matrix. So you consider some state of spins living on one slice and another slice, and you write a partition function as a trace of product of transfer matrices. So it's kind of a discretized version of what we do. So this transfer matrix is usually a pretty easy object. You just stare at it, and then there is an easy theorem that you can show that if this transfer matrix in the spin variables is Hermitian, then your lattice theory is RP. So a lattice theory is RP. It's basically holds if transfer matrix is Hermitian. If you don't know what transfer matrix is, don't worry. Look it up. And so this is a very simple argument. I'll leave it to you as an exercise, but by using this argument you can show that, for example, all classical ON models and many, many other models are RP. You can also show that lattice gauge theories are reflection positive, as was done in early days of lattice gauge theory. So yeah, in good shape. It's easy to check. It's much easier to check RP than to check unitarity of the theory in Minkowski space. That was precisely the point. So okay, once the dust settles, we have a Hilbert space. We have phi's now realized as operators acting on this Hilbert space, and so all of our symmetry generators, which we are still considering Poincaré, which are P mu and M mu nu, are also acting on my Hilbert space. And so now we have the usual operatorial relations. So P mu phi of x equals d mu phi. So until now, P mu was just some sort of machine which was making operators, local operators out of local operators, but now it really becomes a generator acting on a Hilbert space, so which is nice. And so by integrating this relation, you get phi of x plus y equals e to the I pm I mu p mu phi of x e to the minus y mu p mu. Let me take x equal to 0. So now we have to work out the hermeticity relations for our generators. So we have by construction, so since we introduced this theta operator, we have by construction that phi of x Hermitian conjugate is equal to phi of theta x by construction. So by using this relation and this exponentiate formula, you get these interesting relations that P1 dagger equals P1, but Pi dagger equals minus Pi. So now I'm doing my Euclidean theory. I didn't write my i's here. Okay, what I get is that the Hamiltonian is Hermitian, but the momentum generators are anti-Hermitian. So you can write this equivalently by as P mu dagger equals minus theta mu nu P nu, where I view theta as a diagonal matrix minus 1, 1, 1. So okay, that's something that is always confusing when you do Euclidean quantum field theory, that some generators are Hermitian, some generators are anti-Hermitian. You should not be surprised, because we broke rotation invariance when we introduced this Hilbert space, and so this theta operator is presence of theta operator in this hermeticity Hermitian conjugation relation is a consequence of that. So as an exercise, I leave for you to show that Mij dagger is equal to minus Mij, while M0 i's are Hermitian. So what else can you do in this language? Well, one interesting thing that you can show, and actually it's nice that you can show that in full generality in this framework, is that you can show that P1 is a non-negative operator. So you see, we usually say that,
Slava?
yeah?
So I'm confused. Maybe I'm just missing it, but you have P1 and then M0I.
Oh, I'm sorry. Yeah, there was a remark that I should write here, M1I. Yeah. Thank you. So usually we say that in quantum field theory we say, okay, we have the vacuum, and for example, we normalize the energy of the vacuum to 0, and then all other states have no negative energy. But now I don't no longer have, I start from some abstract framework. I just have a bunch of correlation functions. I have, RP. Everything is very abstract. So how do I know? I would like to recover this very natural relation P1 is non-negative. And actually, it's possible to recover it using, so you have to make one additional assumption, which is cluster decomposition. We use this assumption of cluster decomposition, which is an assumption on correlation functions, which just says that if you take a correlation function which has a bunch of points here and a bunch of points there, and they're very far away from each other, then in this limit the correlation function becomes a product of two correlation functions. So this is a natural assumption. And then you can show that under this assumption that P1 is a non-negative operator. And I'm not going to give a full proof, but I'm going to tell you the main idea. So what you have to show, okay, this operator is non-negative. To show this that it's non-negative, you have to show that if you shift by some P1 tau psi, that if you take this exponentiation, then the norm should the norm should decrease. Then the P1 is a non-negative operator. So you have some state here, which is you have some blob which generates this type psi, and another blob, and now you shift it by some. You introduce some shift tau, and then you would like to show that the norm can only decrease. Well, the way you show this is that you take the scalar product, and you apply Cauchy-Schwarz inequality, and so by Cauchy-Schwarz inequality this is less than psi square root times the product of this with itself, which is psi becomes e to the minus 2p1 tau psi square root. And then you keep going. So now you increase we had tau, we had this shift by tau, now we reduce to shift by 2 tau, then you keep going, so you keep increasing the shift, and then in the limit when the shift goes to infinity, then you use the cluster decomposition to show that the correlation function has to factorize. And so this gives you some finite factor which is raised to the power 1 over 2 to the n, where n is the number of times that you did this trick. And so this just tends to 1 in the limit when n goes to infinity, and all the other factors, they give you psi times psi. And so this is how you show in this framework that all states have non-negative dimension. Okay, so we are doing well. Any questions? Yes.
Why doesn't this argument work for the other PIs?
So the question is, why can't I use this argument for the other PIs? Well, because it's important that P1 was a Hermitian operator, because when I apply the Cauchy-Schwarz inequality to this state, I have to conjugate this exponential, and then to argue that I'll get here minus 2p1 tau, P1 had to be Hermitian. If Pi was non-Hermitian, then I at this point I fail. So okay, one more. Any other questions? So one more thing, one more technical point that I.
I have a question.
Oh.
What if there's multiple vectors?
So Greg is asking what's going to happen if there are multiple vector. So if there are multiple vector, then the cluster decomposition is going to fail. So the condition that I'm assuming cluster decomposition is precisely, physically means that there is a single vacuum.
Sorry, but if you compute the correlator in this, usually there is a set of vacuum bases you can choose in which cluster decomposition does hold, even in a situation of spontaneous symmetry. I mean, if you take a linear combination of these vacuum, cluster will fail, but there are, a set of basis vacuum states. They do hold.
Yeah. So let me just paraphrase. So as she is pointing out, okay, if my theory has multiple vacua, then I can still save the day by saying that, yeah, I have multiple vacua, but let me, instead of considering some linear combination of this vacua, I'm just going to put the theory in one vacuum, and if I evaluate all correlations in that vacuum, perhaps my cluster decomposition is going to work. But it's only going to work if my operators don't move me from one vacuum to the other vacuum. If there are operators if there are some local operators which move me from one vacuum to the other vacuum, then my cluster decomposition is still going to be in trouble. So, but okay, I mean, this is a technical point. Let me restrict to theories which have a single vacuum. Okay, so what the technical point that I wanted to point out is that if I'm dealing with, so far I was dealing with operators kind of implicitly which were scalars, but if I have operators which are not scalars, then I have to modify my complex conjugation, and for non-scalars, you can kind of easily convince yourself that the appropriate definition for complex conjugation is that I have to additionally multiply by this matrix theta mu. So I have to do something like omega x dagger equals theta mu O nu of theta x. So this would be an appropriate. So if I want my operators to, so I already know the conjugation relations for rotation generators. If I want my conjugation relation for rotation generators to be compatible with conjugations of operators which are transformed non-trivial under the rotation group, then that's the definition that I have to use. So that's a technical point. Okay.
Should there be a minus sign?
No, here there should be no minus sign.
Even though it's in P?
Well, I mean, theta already contains a minus sign for the tau component. For the tau component, theta contains a minus sign. So this has a very clear kind of pictorial meaning. So if I have a certain operator, if I take a component which points down, then the corresponding reflected operator I should pick a component which points up. It should be really mirror symmetry. Well, if for operators which point along my surface, then nothing happens. Okay, so I think I said a bunch of things, and before going to CFT case, I would like to make a comment concerning cutting the path integrals along arbitrary surfaces. So suppose that I have here I was cutting along straight lines, but sometimes in theoretical physics we like also to be able to cut my path integral along some arbitrary surface, and we would like to still say that that operators inserted below the surface create some state on the surface, and operators created inserted above the surface also create a state on the surface. And you can do this, but you have to be a little bit careful. So let me say what you have to be careful about is that when you do something like that, what are you going to have? You're going to have states created by operators inserted below the surface. They will live in some space V1, and states created by operators above the surface. They will live in some state V2. So these are going to be two vector states of vector spaces of states. And between these two vector spaces of states, I will have a natural pairing. So I can define a pairing between these two vector spaces, and the pairing is just going to be given by correlation function. So that's what I have. And so far, I'm pretty analogous to what I had in the case of cutting along planes. But what I'm not going to have in this case generally is that I'm not going to be generally be able to come up with some mapping, with some dagger operation, which will map V1 to V2. So I will have a space of states V1 and a space of states V2, but they are not going to be in any way isomorphic to each other. They're going to be just two different spaces of states which will be paired, will be dual to each other because of this pairing, but I will not be able to come up with a conjugation mapping. And because I'm not going to be able to come up with this conjugation mapping, I cannot say that my space of states is a Hilbert space. To say that I have a Hilbert space, I have to be able to say, okay, I'll take this state V1 and I compute its norm. To compute the norm of a state, I should be able to take this state V1, I should somehow be able to transform it to a state V2 and compute the overlap. But if I just have a curved surface, there's no way I can canonically take a state here and transform it to some other state there and to compute the norm in such a way that this overlap is positive. It's just, just think about it. If your surface is curved, it's complicated. Imagine you have some, well, this is sufficiently complicated. You already won't be able in general to come up with such mapping. So you have a vector space of states, but it's not a Hilbert space of states. So you have to be a little bit careful. Of course, there are some situations where you can get around this difficulty, and for example, in two-dimensional CFTs, as she explained, you can always pick a metric by doing a Radial transformation. You can basically make any metric flat, and so you can kind of straighten out this this surface, and it becomes again a plane. Just a second, and then also if your theory is topological, as in Greg's lectures, then also this difficulty doesn't matter. But in a general d-dimensional quantum field theory, this would be a difficulty. Yes?
Can I try and chop a second? I've got this line. I can flip it using the time translation chop to have the operator that translates in time from the first slice to the second slice. And then try and use this to define a positivity or inner product.
So Damon was trying to come up with some procedure. So I'm not sure you can do this. So if you try to, there are some naive things that you can do. But what's going typically to happen if you just try to glue this kind of flip and then glue, and then what you're going to end up with is you'll end up with some manifold, which will have the metric is going to have some singularities along this surface, and this you're not going to be able to compute an overlap as a correlator on the Euclidean space, but on some curved space with the metric which is singular on the surface, and that's going to be some infinite object and so on. I'm not sure if that's what you're suggesting, but let's just speak about this offline. Any other questions? Yeah.
So what if I didn't want some curved surface, but I just wanted to use a different coordinate instead of my one coordinate to become my time? Can I just put some eyes in my generators to make that work properly? And what happens to RP?
So Oliver is asking what if I'm going to use another coordinate, not x1 but x2 or some other linear combination, yeah, then you can definitely do it. So as long as you use planes, you can use planes in any direction. And since our theory is by assumption rotation invariance, it's going to work. And but the way you do this transformation is that you don't just take these generators and you multiply them by I. You just take one slicing and you have one Hilbert space, and you have another slicing, and it's like a completely different Hilbert space. You just have to do everything from scratch. And you cannot, in general, you cannot establish a nice, I mean, the correspondence between these two Hilbert spaces.
I mean, if you have rotational invariance in Euclidean space, it seems like there should be some canonical isomorphism or something.
Yeah, so I think you're right. Yeah, so there should be some canonical isomorphism. Yeah, you're probably right. Yeah, that's true. There is some isomorphism. Yeah, so perhaps you can cook something up to make it a bit more explicit, but you don't have to do it. You can just start from scratch, and then I'm not aware of any additional mileage that you will get by cooking up this canonical isomorphism. Okay, so let me then go to the CFT case, and see what happens. And I don't want to be like, I don't want to create any suspense or anything. So we know that, you already know that what we do in CFTs is that we do radial quantization. So in radial quantization, we arrange the conjugation mapping by inversion. So in radial quantization, we introduce a space of states living on the sphere, and let me choose radius 1 around the origin. And so my Hermitian conjugate operator is just implemented by inversion. So this is the formula that you are familiar with, at least in the two-dimensional context. And so if my operator is not a scalar, but it has some indices, then you have to multiply by factors of delta mu nu minus 2x mu x nu over x squared, which is just arises from the Jacobian of the inversion transformation. So okay, so that's what we normally do, and for this to make sense, we already know it's going to make sense if I can argue that that my theory with this notion of hermeticity of Hermitian conjugation satisfies reflection positivity. So if I know that this kind of correlation functions are non-negative, and also more complicated versions when I convolve with f's and so on are non-negative, then I can run the same procedure. I can construct a Hilbert space, and I can work on this Hilbert space, and everything is going to be nice. Now, so usually we assume that this condition. So we have this inversion, we have this positivity, and that's our definition of a unitary CFT. But I'd like to discuss why this is a reasonable assumption. So suppose that I have a Poincare invariant reflection positive theory, which I had here, and so I had this reflection positivity in the Osterwalder-Schroeder sense. And now I happily discover that my Poincare invariant theory is actually also a conformal theory. So I can use conformal symmetry, I can use radial quantization, and I would also like to use this radial reflection positivity using the inversion. So clearly I would like to know if this property of radial reflection positivity is a new assumption or is it somehow a consequence of the property of reflection positivity, of the Poincare reflection positivity that I had? So I hope that it's not an extra assumption. So that's what I would like to explain, why this is not an extra assumption, why this is a consequence, and there are two ways to argue for this. There's one well-known way and one not so well-known way, and let me explain both. So the well-known way is to argue as follows. You take your theory in RD, and you perform a Weyl transformation to the cylinder SD minus 1 times R. So that's what was done in Xi's lectures. And if you do this transformation, then you can easily check that the inversion transformation in RD is going to become on the cylinder the transformation which just changes the sign of the cylinder time under this transformation is going to become this map. And so if we assume, so recall, my assumption is that the theory in Euclidean RD is RP. That's something that I know. Now, if you assume two things, you have to assume two things. First, that the theory which is RP in Euclidean space remains RP on the cylinder. That's the first assumption. Second assumption is that you can perform this Weyl transformation, not just for the partition function, but also for the correlation functions of local operators. Then you're in business. Then you know that your theory is going to be RP in the radial sense. Now, in the 2D case, maybe it's not such a big deal, because in the 2D case, the cylinder is a flat manifold, because you have a circle times R. In the case d larger than 2 that I'm interested in, this is a curved manifold, and so as you realize by now, I don't want to mess around with curved manifolds, and as you've seen in Xi's lectures, it requires quite some technical power to do that. And so I would like to present you another way, which actually I think the cleanest way to convince yourself that there's absolutely no problem that any theory which is RP in the usual Schroeder sense is going to remain RP in this radial sense. And it's an argument which works entirely in RD. So the argument is the following. It uses something which is called north-south pole quantization. And the idea is this: instead of doing a Weyl transformation, you do something which is morally very similar, but it's entirely an RD construction. So you come up now not with the Weyl transformation. You don't change the space, but you come up with a conformal transformation, which maps the point 0 to the south pole and to the point infinity to the north pole. Now, so what is the south and north pole? So the south pole is going to be a point with coordinates -1, 0, and the north pole is going to be the point with coordinates 1, 0. And so I claim that, it's you already know that by conformal transformation you can put 3 points wherever you want, so definitely you can put 2 points, 0 and infinity, wherever you want. So you can put them to these 2 points. Now what happens? Under this transformation, the dilatation generator D goes to some rather important operator which is called conformal Hamiltonian, and it's K1 plus P1. This conformal Hamiltonian. And it was introduced by Lusher and Mack. And Lusher is the same Martin Lusher, which was mentioned many, many times in Tom's lectures. So before he did important work on lattice gauge theories, he did important work on conformal field theories as well. And so this now in this picture we have this radial flow by the dilatation generator. In this picture we have this flow along K1 plus P1, and actually I leave it to you as an exercise that K1 plus P1, so you know the formulas for K1 plus P1, you can check that K1 plus P1 has two fixed points, the south pole and the north pole, and it has these lines of flow. So that's the first thing. And the second thing is that under the same transformation, the same conformal transformation that you will construct, the inversion on the left side is mapped exactly on the Osterwalder-Schroeder transformation theta on the right side. And so we are in business. So we know that if the theory on the right side has a reflection of Osterwalder-Schroeder reflection positivity with theta, and if the theory is conformal, then we go back to the left side, we apply the conformal transformation, and we know that the theory in radial quantization is going to be a reflection positive in the radial sense using the inversion. So that just closes completely the discussion. Any questions about this logic? And so this, by the way, also points out one extra subtlety in the radial quantization reflection positivity. We know that Osterwalder-Schroeder reflection positivity, the theta reflection positivity, it applies to any operator. And in the conformal field theory, it would apply to any operator, to a primary operator or to a descendant operator. They will all be reflected by the same operator theta. Now, if you go to the radial quantization inversion reflection positivity, this formula, this definition for the Hermitian conjugate, as you may know, it applies only for primary operators. And now it's clear to understand why. Because when we go from the right-hand side to the left-hand side, we have to apply this conformal transformation. And if our operator is a primary, then we land on a simple transformation property by the inversion transformation as appropriate to the primary. If the operator was a descendant, then you will land on some, there's going to be a Hermitian conjugate, but it's going to be given by some more messy expression, so which we don't even write down. So that's something to keep in mind. Okay, so now the next step is to work out the conjugation relation for conformal generators. For conformal algebra. So now, okay, from now on, forget about this north-south pole quantization. I'm only going to use the usual radial quantization picture. And so in this picture, I would like to work out in the radial quantization how my generators transform under conjugation. And so the way I'm going to do this is that I'm going to use this formula that I explained last time, that any generator can be given by an integral of the stress tensor And so now if I want to compute the Hermitian conjugate of the generator, I just have to conjugate the stress tensor. Now, what I forgot to say last time, but now it becomes important for this discussion, is that so last time I derived the formula for how stress tensor transforms infinitesimally under Q epsilon, and then I used this formula to derive the conformal algebra, to argue for the conformal algebra. So what I forgot to say is that that formula by itself, it implies that the stress tensor transforms as a primary under conformal transformation in D larger than 2 dimensions. So now it becomes important, because if I know that the stress tensor transforms as a primary, I can use for the stress tensor this formula for the Hermitian conjugation that I wrote here. So I know that this the stress tensor Hermitian conjugation is just E mu mu prime T mu prime mu prime at the point Ix, and then E mu prime mu. And so what do I do now? Well, I have, I just do a change of coordinates. So I call this I over Ixy, and I transform, so my generator Q epsilon, it was written as an integral over some surface sigma. So now I apply inversion transformation. I get some other surface, let me call it I sigma. So I have to keep track of the fact that when I apply inversion transformation, then the orientation of the surface changes. So now I can express, using this formula, I can express the result of the conjugation as an integral over I sigma with some other vector field. So what I'm going to get is that this is equal to the integral over the surface I sigma that I will call sigma tilde ds mu t mu nu epsilon tilde nu. And so what is this epsilon tilde? Epsilon tilde is equal minus I epsilon I. And this minus here comes from the fact that when I do the inversion, it changes the orientation of the surface. So I have to correct for that. And so this relation is all I need to work out my hermeticity properties of my generators. And okay, I leave it as an exercise to show that this relation implies that the rotation generators are anti-Hermitian. The dilatation generator, very importantly, is Hermitian, and P mu dagger is equal to K mu. Okay, so I have like 6 minutes left, and I have a bunch of things to say. So what do I have to say? So the next thing, now we have built up so much stuff that things can happen really fast. So let me discuss state operator correspondence. So I know that my dilatation generator is a Hermitian operator. Actually, it can also be shown by using a similar trick like here, the doubling of the distances and so on, and using cluster decomposition, that just from a reflection positivity, that it's a non-negative operator. So it's a self-adjoint non-negative operator, and so I can apply spectral theorem to it. So let me assume that the spectrum of this operator is discrete. Actually, in all known to me examples of high-dimensional CFTs, the spectral dilatation operator is discrete. So then I can choose a basis in my Hilbert space consisting of the eigenvalues of the dilatation operator. So what are these eigenstates of the dilatation operator? I know that these are some states which live inside the sphere of radius 1, because all my Hilbert space states live inside the sphere of radius 1. They are generated by operators inserted inside the sphere of radius 1. But they are eigenstates of the dilatation generator. So it means that I can apply dilatation generator to them, and they equivalently, they live inside the sphere of radius 1/2, or they live inside the sphere of radius 1/4. They live inside the sphere of any radius. Well, what does this mean? It means that these states are actually local operators living at the origin. There is nothing else that they can be. So, so we have this amazing consequence that any state which is the basis of my Hilbert space can be produced by a local operator acting at the origin. So this is what is called state operator correspondence. So to make this statement, it was important to be able to diagonalize the dilatation generator. So next step is to say, okay, I have my Hilbert space, I have this basis of my Hilbert space which consists of the eigenstates of the dilatation generator. They are primary states and they are descendant states, and maybe there are some other states, but I would like to show that there are no other states but primaries and descendants. So how do I do that? Well, I say, okay, I have my Hilbert space, conformal algebra acts on this space. Let me just decompose it in irreducible representations. Let me look at one irreducible representation of the conformal algebra, and within this irreducible representation of the conformal algebra, I know that I have this commutation relation dk mu equals minus k mu. And this commutation relation says that by acting with k mu, I lower the eigenvalue of d. But as I told you, d, it can be shown in full generality that d is a non-negative operator in an RP theory. So I know that this has to stop, and so every irreducible representation that I will have in my theory will contain a state which is going to be annihilated by k mu. And so this this state is going to be called primary state. And in the first lecture, I gave you a different definition of the primary state. I said that the primary state is the one which transforms as phi tilde of x prime equals 1 over omega of x to the delta rho of r of x phi of x. And actually the two definitions are equivalent. And okay, I leave it as an exercise to see why they are equivalent, but as a hint I can tell you that the key to understanding this is to notice that k mu vector field vanishes to the quadratic order at the origin. And so if you look at this formula, and if you look at what that formula does near the origin for k mu vector field, and you notice that this omega is trivial for k mu and r is also trivial for k mu near the origin. And so this transformation, in the case of special conformal transformation, it just does nothing to phi near the origin, and that's precisely what we mean by saying that k mu acting on phi at the origin is gives you 0. And so what we have then is that we have shown that our Hilbert space decomposes in a direct sum of irreducible representations. Every reducible representation has a lowest weight state, which is the primary, and then it's built by acting on the primary with p mus. And acting with p mus means taking a derivative. So I have shown that every state is either a primary or a descendant of a primary. Okay, so I'm almost out of time, but one last thing that I'm going to say is that in this language that we just introduced, the existence of operator product expansion becomes a triviality, because what I just said is that any state living on a sphere can be expanded as a convergent sum, convergent in the sense of the norm in my Hilbert space, with some coefficients as a sum of local operators with certain dimensions delta I living at the origin. But okay, this is for any state, but just for simplicity, I can apply this very general result to a state which is generated by two operators inserted somewhere inside this unit ball. So if I apply it to two operators, I get what we call operator product expansion. And, so I wanted to tell you about the unitarity bounds, but I guess I will have to do it next time. So I'll stop here.
Any quick questions?
The first lecture you said that there were large classes of non-unitary theories where states could be organized into primaries and descendants as well. Does this shed any light on what those theories might be?
So the question was, so in my reasoning today, I used a lot Hilbert space language and unitarity and spectral theorem for the operators, but we know that some of the conclusions that we obtained hold also in non-unitary theories. For example, there are in many non-unitary theories which we know explicitly and we understand, it's also true that states decompose into multiplets of primary plus descendants. And so why is that the case? Well, yeah, I don't know. It's a mystery. It's a mystery. So because we also know of some other non-unitary theories where it's not the case, because there is logarithmic conformal theories where the structure of multiplets is more complicated. So it would be nice to have a set of general physics criteria which would allow us to say like which non-unitary CFTs are simple and which ones are more complicated and so on. But as I say, it's such a general theory doesn't exist. So it's an open problem.
All right, let's thank Slava again. See you at 2 p.m.
Can there be a reflection positive theory that does not have any primary?